Okay, I think we're far enough in. Why don't we switch to now tour through interesting things people have done. One that was emailed was Daniele sent a note about his uh, the board he made for this week. So Danielle, are you connected?
Yes.
Hi, Neil.
Yeah, go ahead. So tell us what you did.
Yes, before I
Sorry,
started
sorry, your volume is a little bit low. Can you come closer to the microphone?
Yes, okay. Okay. Before I was thinking about design my own board. I made the FabAcademy following the tutorials. So this is
Sorry, let me ask you a question. Um,
yes,
are you the board? How did you make the board? Is this done with the fiber laser?
yes, of course, yes. We
Okay, so
made
are you using that routinely now?
yes, yes. We are we find the right settings and so on. Yeah, we have a very stable process to
Okay,
make.
how long does it take for the laser to mill that board?
Sorry, quanto
How long does it take?
For a normal fab kit, like 30 minutes.
Yes, more or less.
Okay, now first let me explain to everybody else. Trotec makes the Flex. And so the Flex 100 is the CO2 laser, which is 10 microns, but it also a fiber laser that's 1 micron. But that brings the cost up to about 40K. So it's about 30 to 40K, much more expensive, but you get 2 laser wavelengths and it lets you do this. Now, one caution, remember, when you do it, the copper doesn't disappear. You're evaporating it and you're depositing it. So just one thing to track is the copper is going somewhere. So you want to keep an eye on your bearings and your optics to see if you do a lot of this, if there's any issues with the copper deposition.
Okay.
So just keep checking your bearings, keep checking your optics, because you need to be aware when you're doing this, the copper is ending up somewhere. It's not vanishing.
Okay.
Okay. But so
Okay.
go ahead. So you designed a fab kit.
Okay, this is the first attempt of the old fab kit.
Uh-huh.
And so I was not satisfied about this fab kit, so
Yep.
I was thinking about a new one that is more compliant, standard like Arduino. It's very close to Arduino. So here you can see the schematic and the board of Eagle. As you can see, there are almost rect traces and plenty of space to easy soldering. So
Okay. By the way, just let me explain a minor detail. Uh, when you're milling, it's fine for traces to do that. When you're etching traces in commercial PCBs, for etching is bad at sharp corners because they etch at different rates. So if you look at etched PCBs, you'll see they avoid sharp corners because you get a different etch rate, but that's only if you're doing dense boards in volume production by etching. So I make sharp corners because I'm milling. When you're doing dense traces with etching, you try to avoid sharp corners.
okay.
And for your process, it doesn't matter. The laser doesn't care.
Yes, okay, of course.
Yeah.
So
Okay.
this is the first board that is working.
Nice.
I smoked about 5 boards before getting this one working.
Okay.
So when I made it, also I listed the pieces with the BOM, and These are the main improvements. So as you can see, this board is very close to Arduino, and you can program with the default Arduino ID without modifying any files or getting any patch. So this is the mapping for the Arduino pins, and also some connection schema for programming it with FabAcademy. These are the boards from my other fellow students.
Nice.
Here are some videos about programming the board and using it with multi-Wii firmware, and also with Telemin. Okay, the examples from Arduino. The Telemin example from Arduino.
Okay.
So this is an UMU connected to satshakit, and as you can see, you can see the data while the EMU is moving. Okay, so this is the other video. Okay, that is set up. We programmed our satshakits with FabAcademy with no problem. Okay, and this is my exercise for this week. I made a little radar with two common sonar sensors.
Yeah. First, just in English, it's a sonar, not a radar. Radar is electromagnetic. Sonar is acoustic.
Okay, acoustic sonars, yes, okay.
Yeah,
and,
okay.
These sonars are connected to a recycled stepper from an old scanner. And so I modified the satshakit to put inside also.
Sorry, periodically the desktop drops, and I need to I'm going to interrupt for a moment. I have to just restart the desktop. Let me reconnect the computer. This will take just a minute. About halfway through class, something okay, so I'm going to restart it here, then I have to restart it here. And then I have to go back into the bridge to re-add it. Okay, and then let me, okay, so I've got the desktop added back in, so go ahead, you were going to show it? So Danielle, go ahead.
So, I don't know if you can see, this is my experiment while it's working.
Yeah.
And this is the board that is a satshakit with an ULN 2003 controller for stepper. Okay. So also it's easy to modify, to extend this board to do something else like this. Okay.
So then, do you have something showing this? Let's see, the sonars.
Yes, but I don't know if I can take the computer here to show.
No, I'm gonna do your video.
In the video, you can see the data that I displayed in the serial monitor. So it's real-time data. In the video, I put an obstacle, so you can see that the distance is reduced. Okay. It's the last video.
So you're just looking at the serial data coming back?
Yes, just this.
Okay. Then are you using a library, or did you write the code to talk to it?
I used the new ping library for getting data from these acoustic sensors, sonars. Okay. And
Okay.
so I wrote an Arduino sketch basically. And this is also the first prototype of the flight controller of my final project. So,
So let's come to the final project in a moment. Just a note on the sensor. These sensors are really easy to talk to, just to explain to everyone. All you do is you turn a pin on and off, and then you time another pin.
yes.
And so the library is fine, but you don't feel like you need to paste in a library. It's really easy. You just drive one pin and you read the other pin to talk to these. Yeah. Okay. So now talk about your project plan. Let's see. Remind me about your background.
Yes, I'm an information technology engineer. I work for Engineering Informatica. That is one of the largest company for software developing here in Italy.
Okay.
And, but at home, I always enjoy experimenting something, as you can see from the About page. And so I enjoyed this FabAcademy a lot. I staying here at the night alone to do something like this board. And so.
Good. Okay. And then what do you want to do for the project?
For the final project, I want to build a smart drone, a smart quadcopter, and that can have a lot of smart functionality like cooperating and like self-assembly. It's maybe it's just too ambitious, but I will try to do it.
Yeah. Now that's a good example. You could do the whole project, but for the final projects, it's okay to collaborate in complete systems. So like one complete system is navigation and controls. Another complete system is power electronics and propulsion. And so another complete system is the large-scale mechanical structure. So you could collaborate with somebody as long as you have separable projects where you can show that you do a mix of everything.
Okay, if anyone is interested, also who is listening now, it's not a problem. Just write me an email.
Yeah. Now, why are you looking at the Mega 2560?
Sorry?
I'm looking at your page.
Yes, because I for the serial and the pins, because there are many pins and in this kind of microcontroller. So but I found that it's very difficult to solder and to manage. It's big also. So I want to do a small quadcopter, so I don't need all of these. So
right.
I will fall back to the 328 P.
Yeah. But there's a couple options. If you need more processing,
yes.
There's options on both sides. So in a couple weeks, we're going to talk about networking.
Okay.
So one thing you can do that I like is instead of one big processor, you could have like 5 small processors.
Yes, this is what I want to do for the and the sensor boards.
Right, but they can be even smaller than the Mega, meaning you could have one tiny 44 doing, each function gets a little sensor, and then each process thread gets a sensor. And so a neat thing to do is have every single thread in a program and every single sensor have its own processor and make a network. And that's a really good way to do it because it's easy to debug and it's easy to modify the system.
Yes,
so networking lots of little processors. And in 2 weeks, we're going to talk about, where are we? in 2 weeks, we're going to talk about networking, or 3 weeks, networking processors.
Okay.
Okay.
So,
The alternative at the opposite extreme, if you really need many more pins and you need much more processing, one of the a good way to do that is here, the let me open these. These are dev boards for the STM32, and the dev board is only $10. It's an STM32, and you can snap this off. This is the in-circuit programmer.
okay.
And so this is the F3 that has good analog peripherals. Then there's the F4 that has faster digital peripherals. But these move up to the STM32 ARM, and the dev board, including the programmer, is only $10. And so this is a good step if you need more processing power than the AVRs. And those work with the embed workflow.
Okay, I understand, but for the processing power, I'm considering also a smartphone for the high level data elaboration, data calculation.
Yep. Okay.
So this is maybe only the part for the sensors.
Okay. Good. Okay, that all sounds fun. That's a nice project. Good.
Bye.
15 minutes left. Who else?